Okay, so carrying on with the nomenclature unit, we are going to look at peroxides. And if we were given the name of sodium peroxide and we were asked to try and solve for the formula, this is the method that you would use. So first you would pretend that the per of the prefix peroxide doesn't exist. So you would just write out a regular sodium oxide. Well, we know that sodium has an Na symbol and a 1 plus charge. Oxygen has an O symbol with a 2 negative charge. So to write out a regular sodium oxide, we would cross over the charges and it would become Na2O. So we can see that here. This is a regular sodium oxide. It has the formula of Na2O. So we don't want a regular oxide though, we want a sodium peroxide. So now we just keep our regular sodium oxide formula and we add 1 extra oxygen and we keep it like that. We don't cancel it. So now it's Na2O2. So in the past we said that if you have the same subscript of 2 and 2, you can cancel it and it would just become NaO. But in order to show that this is a peroxide, we need to show that 1 extra oxygen has been added. It's always 1 extra oxygen that's been added. So if we look at another example of barium peroxide, we're going to pretend the per prefix doesn't exist at the beginning, and we're just going to write out a regular barium oxide. So we know the symbol for barium is Ba and the symbol for oxygen is O. The charges are a 2 plus and a 2 negative. So when those charges are crossed, we're left with BaO. So in this case, now that would be our regular barium oxide formula, which we can see here. But in order to make that a peroxide, we have to add 1 extra oxygen, and now we can say that this is barium peroxide. 1 extra oxygen has been added. Looking at hydrogen peroxide, this is probably a household product that you may have. So we start out by canceling out the per, pretending that doesn't exist, and just writing a regular hydrogen oxide. So hydrogen has a 1 plus charge, oxygen has a 2 negative charge. When those are crossed, we get the regular formula of H2O for water. So then adding 1 extra oxygen, we get H2O2. We don't cancel those subscripts, we keep them to show that it is a peroxide, and we're left with H2O2. Our last example is lead 2 peroxide. So they're telling you that the charge on lead is 2. So that is Pb with a 2 plus charge. And then our oxygen has a 2 negative charge. Crossing those, you would get a regular oxide formula of PbO. And then making it into a peroxide, we add 1 extra oxygen. So that's how you go from the name to the formula. And then I also want to show you, if you were given the formula, how would you go back to the name? So if we were given the formula of PbO2, our first step would be to uncross the charges. So that 2 originally came from the Pb, and this little 1 that's not drawn originally came from the O. So we can say the original charges were Pb2 plus and O1 minus. Well, we know that the charge of O is never 1 minus. It's always O2 negative, and Pb is 2 plus because they told us that in the question. So something must have changed here for this charge to go from 1 to 2. So if this was our original, this is what it should be, right? We know that the charge on oxygen should be a 2 negative. And if we were to cross those charges, that formula would be PbO. But we can see in our given formula, it's PbO2. So that should indicate to you that because there's 1 extra oxygen than there should be, that makes this a peroxide. So I can also show you, we've got some example questions here, and let's just take a quick look to see another example of that. Okay, so in this question, we've got MnO2. So this is a peroxide example, but at this point, we probably wouldn't know that until we kind of look further. So I've got MnO2, this is my formula. My first step is always to uncross the charges. When I'm looking for the name of something, you always want to uncross the charges and see what the original numbers were. So that means that Mn had a 2 plus charge and O had a 1 negative charge. Well, right away, that is an indicator O never has a 1 negative charge. Something must have happened, and this isn't just a regular oxide. If this was a regular oxide or a regular situation, this would have a 2 plus and O would have a 2 negative. So it should have a 2 negative, which would make it MnO2, 2. And these would have canceled out to make MnO. So this should be our formula. but we can see in our question that is not the case. We've got O2. So in order to get that second oxygen, it must be a peroxide, MnO2. One oxygen was added to that formula that it should be. So this would make that name manganese. And because this is a transition metal, we have to indicate that charge of manganese, which is a 2. And this is a peroxide. So this is what we would call this as a peroxide, because we know that there was one extra oxygen added from the formula that it should have been with the -2 charge. Okay, so back to our first page for the nomenclature, the part B here. It says that if the valence is not indicated. So for only 3 elements of copper, lead, and manganese, sometimes the names will be listed without the valences or without a Roman numeral. So in the past, we've said that if you have a transition metal, you have to have a Roman numeral. Those transition metals are in the middle of the periodic table, and they have multiple charges, multiple valencies. So you would have to indicate which one you're talking about using a Roman numeral. But in this case, we've got 3 examples where a Roman numeral is not listed, and we can assume that the charge that they're talking about is a 2+ charge, because that's the most common valency for these elements of copper, lead, and manganese. Only these 3, though, that it shouldn't be listed for. If it's not listed, you can assume a 2+ charge. So we've got an example of manganese bromide. We can assume that the charge they're talking about for manganese is 2. So that makes the formula MnBr2. Same with copper 2 chloride. Copper is one of the 3 elements that doesn't need a charge listed, so we can say if it said copper chloride with no charge listed, we would assume that the charge on copper is 2. We would cross it with the charge of Cl, which is 1, and you would get the formula of CuCl2. The last one is lead. We don't have a charge listed, so we're assuming it's lead 2, and iodide has a charge of 1, so you get a formula of Pbi2. So there's lots of different examples here of peroxides, as well as some examples of using elements that don't have a formula or a Roman numeral listed. There's also this page of examples as well that you can try out for practice before moving on to the next concept. Okay, the next section is other radicals. This is also referred to as polyatomic ions. The first one we're going to talk about is ammonium, and the formula is NH4+. That means it has a valence of a 1+ or a charge of 1+. Anything that has a positive charge is considered a metal. That means it's going to lose its electrons, whereas a negatively charged ion is going to gain electrons. Any positively charged ions are considered the metal, and they always come first in the formula or in the name, whereas the negatively charged ions are the nonmetals, and the nonmetals come second in the name. So if we're looking at ammonium of NH4+, we're considering that to be our metal. If it bonds with chlorine, which we know has a -1 charge, so when we cross these 2 charges, we're going to get a formula of NH4Cl. So normally this NH4 would have to be in brackets, and because that's showing that that is all one ion together. That H is bonded also with the N. But because this time when we're crossing them, that charge is a 1 and the chlorine also has a 1 charge, you can just write it as NH4Cl because each of those has a 1 charge. In any other case, you would have to keep the NH4 in its own brackets. So we haven't looked at these examples yet, so I'm just going to move on to our second one, which is hydroxide. This is our second polyatomic ion. The formula is OH negative with a valence charge of -1. So when I write this out, this is an OH group, and it's a -1 charge. So the OH has to be in brackets, and the charge of that whole compound is -1. Because this is a negative charge, we can assume this is the nonmetal, and the nonmetal always comes second in the equation. So that's why our hydroxide is going to come second in our equation, or in our name. And if we were bonding this with a metal of a +1 charge, we can cross the charges over and it would become NaOH 1 and 1. Now because they're both 1s, you don't have to write the brackets, you can just say NaOH, but in any other case, if they're not 1s, I want to see the brackets around the polyatomic ions to show that you do know they are polyatomic ions. So in the second example, we've got ammonium hydroxide. So we're bonding everything that we learned about the first example with the second example now. Ammonium was our positive charge, so the positive ion is going to come first in the equation, and the negative ion is going to come second. So because ammonium has a 1 plus charge and it's crossed with a hydroxide that has a 1 plus charge, we don't need the brackets and we can write NH4OH. But in our example of number 3, we're bonding the metal of iron. So iron has a 2 plus charge, they're indicating that with the Roman numeral, and our hydroxide has a 1 negative charge. When you cross those two over, we have to remember that this OH is in brackets, and that means that it's going to be Fe bracket OH2. What that's really telling you is that this little 2 applies to everything inside the brackets. So there's 2 oxygen atoms, and there's also 2 hydrogen atoms. So that's why these brackets are so important, because if there was no bracket, if it just said FeOH2, that would be indicating that there's only 2 hydrogens, but there's also 2 oxygens, so you have to have the brackets included. They give another example of copper 1 hydroxide, and because both of these charges are 1, you can just write the formula as CuOH. So moving on to some more polyatomic ions, we have an acetate ion. This is a polyatomic ion, and the formula is CH3COO with a valence of -1. So in this case, we've got a negative charge, so it's always going to come second in our name. So in this case, we've got calcium acetate. So calcium is the metal. It's got a Ca2 plus charge, and our acetate ion in brackets is CH3COO with a -1 charge. So those charges are crossed over each other. I'm going to do that, there we go, to the opposite sides. And you can write a Ca now has a little 1 there, and then CH3COO in brackets with that little 2 from the calcium. So that indicates that there are 2 atoms of each of these in the brackets. So we need to have those brackets there. In the example here, they write the Ca after the acetate. I would like you to always write it before. It doesn't matter either way, I guess, but I would like the metal to come first and the nonmetal to come second, which would be the acetate. So your final answer for that would be CaCH3COO bracket 2. So that would be your final answer that I would box in there. And we've got some other examples. They have iron 2 acetate, so the iron has a 2 plus charge. It's crossed with the acetate ion of 1 negative, and again, I would like that to be written as Fe bracket CH3COO2. So going along, that would be the same thing. Ammonium has your 1 negative charge. Acetate also has a 1 negative, or ammonium has your 1 plus charge. Acetate has a 1 negative charge. When you cross those, that would look like this with the NH first. Another example, we've got permanganate, so MnO4 negative. This is a polyatomic ion with a valence of 1. So when you cross that with a metal of a positive charge, you would get a permanganate is your -1 charge, cross it, and get a formula of KMnO4. So there's many different polyatomic ions. This is kind of a chart with some examples of them, just being bonded with other things. So we've got dichromate, we've got chromate, and cyanide. And basically you don't have to memorize any of these specifically. You're going to be given a chart, and I'm going to kind of pull that chart up here. So this is the chart that you will be given on any test or quiz or exam. And so you don't have to memorize them, they're all listed here. So I would use this chart to do your homework questions. There is a homework questions page posted here using polyatomic ions and writing the names of them. And I've also written the answers out for you to look through that. But really try and write them out yourself before looking at the answers. Those are just posted as checkpoints to make sure that you're on the right track. As always, email me with any questions.